In this video, we're going to start the last part of our chapter, which is drawing electron configurations using the Schrodinger model. You can recall earlier in the year, or earlier in the chapter I should say, we did electron configurations with the Bohr model. Because the model itself is incomplete, the electron configurations only give us partial information about how our atom behaves. The Schrodinger model is a better model, therefore it creates better pictures of what electron configurations are and what the behavior of the atom is actually going to be. Let's begin this process with a quick rundown of the learning objectives in this video. First of all, we're going to recap how to do electron configurations using the Bohr model itself. I want to make sure you remember the old way of doing things so that we can see how this new way is different. Just like the Schrodinger model modified on the Bohr model to create a better picture of the atom, we're going to create modifications to the structure of the electron configurations to make the new configurations using the Schrodinger model. Lastly, we'll talk about something known as box diagrams. If you recall, when we're using the Bohr model from before, which is what this picture is all about, we simply placed electrons right on the picture of the atom itself. Unfortunately, if you recall, the Schrodinger model pictures are far more complicated. Instead of trying to place electrons on that picture and making a big mess of things, we instead place the picture or the electrons in a diagram known as a box diagram. So the box diagram is simply a picture that allows us to show the organization of electrons without having to keep track of all the crazy stuff that goes along with those complicated pictures. Finally, once we get an idea of what a box diagram is, I'm going to give you an introduction of where this discussion is heading next. We need to talk about how to build box diagrams from scratch, and we also need to talk about filling rules for placing electrons into box diagrams. And all those things are things to come in videos in the future. So to start us off, I want you guys to remember how to do electron configurations with the Bohr model. What I'd like you to do is draw me a Bohr model for the electron configuration of a chlorine atom with a charge of 0. Pause the video. Take a few minutes to give this a try on your own. We'll go over the answers in a second. Really quickly, to recap this process, we start over here on the left by calculating the number of electrons using our equation we've had pretty much since the beginning of the year. Charge is equal to protons minus electrons. The charge is told to us in the chlorine atom itself. Protons we get from the periodic table is 17, and we're interested in how many electrons are needed to place in our model. We do our algebra here. It's relatively simple. We find out we need 17 electrons. Once you know that, the order of business then is to draw the necessary number of rings. We talked about some tricks to do that, and then populate those rings with the 17 electrons we just calculated. Remembering, each ring holds a certain quantity of electrons, 2 in the first, 8 in the second, and 8 in the third. We end up getting 2 electrons in the first, 8 in the second, and then the last ring only needs the last 7 electrons to get us to our total of 17. What we talked about with this picture is then this configuration gives us hints or indicators as to the type of chemistry that our atom is going to undergo. For example, this atom is missing the last electron in the last ring. That's something that atoms generally don't like, and as a result, chlorine atoms generally undergo any type of chemical change that will get them that last missing electron. As I said, the purpose of an electron configuration is to tell us about the chemistry of the atom before we're actually working with the atom itself. So it's a way of predicting that chemical behavior. This configuration is going to get better when we work with the box diagrams, and as a result, we're going to get even more information out that's going to tell us about this chemical nature of chlorine atoms. To continue this process then, we're going to start talking about some of the modifications needed, and here's where we're going to start writing down some details about what specifically needs to happen in order for us to transition from the Bohr model into the Schrodinger model. To start, we'll do a little general overview here. The Bohr model itself was fundamentally correct. It had a lot of great ideas in it, and sometimes I feel poor old Bohr gets a poor shake, and people tend to think that it just makes a bad model. It was the best model at the time. Unfortunately, though, now that we know about more what's going on, we recognize that the Bohr model is a relatively coarse picture of the atom. It's a relatively general idea of what's going on, and we require a lot more specifics and a lot more detail. A great example of this generality is the fact that the Bohr model couldn't explain all the jumps that we see in spectroscopy. Remember, each electron jump corresponds to a line on our spectrometer, and we were seeing lines in the spectrometer that didn't seem to match up to the atoms that we were talking about. Because of the coarse picture this model created, it couldn't explain everything that was going on. The Schrodinger model then, and we can see the picture on the right, was modified from the Bohr model to include all those new ideas we've talked about in previous videos. Heisenberg's uncertainty principle and wave-particle duality. And all of that was folded together into something known as the wave equation. Now the most important thing you can take away from this discussion is the fact that all of this stuff really caused us to replace those rings or shells from the Bohr model, these guys over here, with the idea of three-dimensional orbitals. And we now know the electrons don't travel in rings, they instead travel in orbitals like the 2s orbital, the 1s orbital, or the 2p orbital. Therefore, the work we have to do today is translating the process of placing individual electrons on individual rings to placing individual electrons within individual orbitals. So let's start getting into some of the details here. First of all, those Bohr rings, or those shells we talked about, represented really average energy levels. It represented basically what seemed to be a group of different energy levels all smushed into one. What it turns out is that there are actually many what we'll describe now as sublevels. What seemed like one big average level was made up of a bunch of tinier levels, and as a result, we were missing a lot of this fine detail. Those sublevels were really the atomic orbitals we've been talking about all along. And one ring of the Bohr model really is represented by many orbitals. So the rings are now subdivided, and that's the word we tend to use for this. Those individual rings are subdivided into many orbitals. Now the number of subdivisions you get is based on the number of ring you have. And there's a pattern to this, but you should jot all this stuff down. For example, ring number 1, the innermost ring, divides into one orbital. That one orbital is an s orbital, and we call it a 1s orbital because it associates with ring 1. Ring 2 then divides into two orbitals. We get an s and a p, each labeled with a 2. Ring 3 divides into three orbitals. We get s, p, and d. And then finally, ring 4 divides into four orbitals. We get all four s, p, d, and f. Following this pattern, you might expect then ring 5 to have 5 sublevels and ring 6 to have ring 6 sublevels. But in actuality, once we hit that 4 maximum number, we find out that all rings after ring number 4 only have 4 orbital types in them. And again, that's going to be s, p, d, and f. The reason we're limited to 4 is because there are only 4 naturally occurring orbital types, s, p, d, and f. There are hypothetical g and h and I orbitals. However, we don't have any atoms that use that, so we stop the process at 4. So this gives us an idea of how these subdivisions actually occur. Seeing that description in text is also a little hard to understand, therefore here's a graphical way of showing the exact same information. And we can take this picture and separate it into two separate sides. We got stuff going on the left and stuff going on the right. The left side we see a very small number of general levels. This side represents energy levels in the Bohr model. And over here we see those levels subdivided, therefore this represents energy levels in the Schrodinger model of the equation. And what we're seeing here is exactly what we talked about before. What used to be one average energy level has now split into two more specific sublevels or orbitals. We see that the 2s orbital is actually a little lower in energy than the ring 2, and the 2p orbital is a little high. And as we go higher and higher in energy levels, we see more and more of these subdivisions occur. Now before we get into some of the details here, just like before when we could place electrons in the individual rings on the Bohr model, we can go over here and we're going to be placing electrons in the individual sublevels. Because there are more sublevels to deal with, there are more different places to place the rings, and as we'll see in the future, there are more rules that govern this placement. One last thing I want to point out is you do start to get some complex stuff happening here. We can see up here that the ring 4, when it splits up, starts to overlap the ring 3, meaning back in the day it was very easy to place electrons in increasing rings from 1 through 4. Unfortunately, with the Schrodinger model, that order of orbitals starts to get very complicated, and this is something we will definitely need to deal with down the road when you guys are making your own Schrodinger model diagrams. Now let's take this a little bit further. We talked about now how the original rings were split into sublevels. Where it goes a little more complex is the fact that those sublevels themselves split further into many individual separate orbitals. So these levels split up into sublevels, and the sublevels split up even further into separate individual orbitals. If you recall, back before we went off to break, we talked about drawing pictures for each of the orbital. And when we drew s orbitals, there was a picture that we had for it. When we drew p orbitals, there were actually 1, 2, 3 pictures that went for that. And when we went with d orbitals, there was 1, 2, 3, 4, and 5 pictures. So when we talk about a p energy level, it's not really made up of 1 orbital, but of 3. And when we talk about a d energy level, it's not made of 1 orbital, but it's made of 5. And again, we're getting more and more and more specific about where these electrons are individually going to be placed. All that information then gets folded into the concept of a box diagram. And what a box diagram is basically an electron configuration that is made based on the rules associated with the Schrodinger model of the atom. So now let's talk about what some of those rules actually are. First of all, those complicated orbital pictures that we just saw are too much to try and draw every single time we do this. As a result, we instead represent those orbitals with individual boxes, hence the term box diagram. Each of those boxes, meaning each of those orbitals, holds a maximum of 2 electrons. Just like the rings had a capacity, the orbitals have a capacity. Electrons are now represented by arrows in the diagram, and we'll talk a little bit more about why this is necessary in some later videos. In the Bohr model, we could use a lot of different things: dots, E's, numbers, etc., etc. In the box diagram model, we're going to use specifically arrows. We're going to see that the rings from before, as we've already talked about, split into different number of orbital sublevels. And we're also going to see that each of those sublevels have a certain number of boxes in it that matches the different numbers, or the different types of pictures that we drew for that individual group. And this is something we were talking about in the previous slide. Now, all of this stuff can get a little complicated all at once. What I'd like to do on the next slide is try and summarize it using a quick table. So take a second before we start. Jot this table down. What we're going to do is organize the information from a couple of the previous slides all into one place. Now, if you recall from before, when we're talking about number of types of s orbitals, that's the number of pictures you drew, and there was only one type of s orbital, and that was the sphere we draw. Each orbital has to be represented by one box, so if we have one orbital in our s level, we're going to need one box to represent it. And if you recall from before, each orbital in each box holds a maximum of 2 electrons. One box means that an s level can hold a maximum of 2 electrons. Going back again, p orbitals, there were 3 different types of p orbitals, one going up and down, one going left and right, and one going front and back. 3 different types of orbitals means we need a box to represent each one, meaning we're going to need 3 boxes. Each box in each orbital holds 2 electrons, which means a p energy level can hold a maximum of 6 electrons. Repeating this process with D and F, there were 5 D pictures, meaning we're going to need 5 boxes to represent it. 2 electrons in each box means a total of 10 electrons. And then finally, with F orbitals, there were 7 pictures we drew, meaning we'll need 7 boxes to represent each of those individual orbitals. 2 electrons in each box means a total number of 14 electrons. As we said, just like the Bohr model had limits to how many electrons fit in each shell, now we can clearly see that the Schrodinger model has limits to how many electrons can be held in each orbital sublevel. And this is something that's going to be very important for us down the road. Now let's fold all of this into the actual diagram itself. This picture on the screen right now is a blank box diagram showing the orders in the correct order based on their energy level, showing the correct number of boxes associated with each one. And what we would do with this picture is to take some time, figure out the number of electrons in our atom, and then place those electrons using a set of rules into the box. When we're done, we'll have an arrangement of electrons that we'll then be able to use to predict the behavior of this individual atom. I very strongly encourage you to take some time. On the bottom of the page, there should be a link that'll bring you to a blank version of this document. I recommend printing that out and having it available, and we'll be using this in class to do our first couple examples. But this is going to be the template that we're going to be using to do all electron configurations using the Schrodinger model, which is basically all the electron configurations we're going to be doing for the rest of the year. We can zoom in a little bit and we can see an example here of one of these box diagrams filled in. Notice this particular atom only had enough electrons to fill up to the 3p orbital, and we notice we didn't finish that 3p orbital. We can see some detail here in this top orbital showing us specifically what's happening with those individual electrons. Namely, that we get a pair of electrons here and we get 2 lone electrons here. And later on, we're going to use this idea of pairs versus lone electrons to predict the behavior of this atom. We're not going to get into that much now. All we're going to focus on right now is that there were a set of rules to place these electrons in appropriate places, and there's a certain number of electrons. In this case, it's going to be 16 if you counted them up, meaning that this could be a configuration for a sulfur atom with a charge of 0. Our job in the next couple of videos is going to be learning how to accurately place electrons to create a configuration like this to represent a particular atom. So moving ahead. A lot of this might be a little overwhelming. Hopefully it wasn't too bad. I just want to talk a little bit about things that we're going to be doing in the next couple of videos. First of all, those box diagrams that we were talking about, you get one copy from me, but unfortunately the rest of them you're going to have to build on your own. What I do not recommend is trying to do this from memory. That would be a silly thing to do. What I'll be showing you in the next couple of videos is the fact that there's a trick for building the box diagrams. Once you have the box diagrams built, then you have to correctly fill them with electrons, and another video is going to discuss what we're going to describe as filling rules, the proper way to place electrons so you get the correct configuration. Finally, once we have a good idea of how to make our own box diagrams, we got to talk about what to do with them. Your goal will be to compare and contrast box diagrams of different elements and substances to compare and contrast their chemical properties. And we'll be able to explain chemical behavior based on the arrangement of electrons we're going to be seeing. This information is going to be stuff we tackle in future chapters. And in fact, I would say almost all the chapters from now until the end of the year are going to focus on this topic. So that brings us to the end of our video for today. Just to go over a quick list of things you should be able to do. Unfortunately, not so much yet. More of what we covered today is some of the basic knowledge, and our videos in the future will cover more of the actions you'll be associated with this. However, there's some things you should know about. First of all, we should know how the Bohr model was modified into the Schrodinger model and how we changed the rings into what we now call a box diagram. You should also be able to describe what a box diagram is and be able to recognize the basic components of a box diagram, the arrangement of the levels, the number of boxes we get per level, all of that general information we've talked about. What you should have in front of you right now is a printed version of that blank box diagram that is definitely something you'll be referencing back to multiple times over the next couple weeks. In class, we're going to spend some time going over these ideas and, more importantly, practicing making box diagrams of our own.